Every year, millions of cars reach the end of their lives. Once they ruled the highways, now they sit silent, rusted, forgotten. But here's what most people never see. An old car doesn't just disappear. Right now, across the planet, about 27 million cars are recycled each year. That's roughly 74,000 vehicles every single day, transformed from end-of-life junk into brand new steel for buildings, bridges, wind turbines, and even tomorrow's cars. We're stepping inside a massive recycling facility to follow the complete journey of a car's final transformation. And what happens inside these walls is far more powerful than you expect. It begins quietly. Flatbed trucks roll through towering gates, carrying vehicles that will never drive again. Flood-damaged engines, twisted frames from collisions, machines declared beyond repair. They look finished, but this is not the end. Before destruction begins, precision takes control, because you can't simply throw an entire car into a shredder. Every vehicle is carefully inspected. Fluids are drained: engine oil, coolant, transmission fluid, brake fluid, fuel. These liquids are stored separately, recycled, or treated to prevent environmental contamination. The battery is removed to eliminate chemical hazards. Airbags are neutralized to prevent accidental explosions. Catalytic converters are extracted, containing precious metals like platinum and palladium, which are refined separately. Even wiring harnesses may be stripped for copper recovery. Piece by piece, the car is reduced to its structural skeleton. Only when hazardous components are removed does it move forward. And that's when the quiet yard transforms into controlled chaos. A massive steel claw descends and grips the vehicle's frame. The car is lifted high into the air and carried toward a crushing chamber. This machine is pure force, a hydraulic press capable of exerting hundreds of tons of pressure. The car is placed inside. The steel walls close in. Slowly at first, then relentlessly. Metal groans under stress. In less than 60 seconds, a 2-ton vehicle is compressed into a dense slab of twisted steel, barely a fraction of its original height. But crushing isn't the end. It's preparation. Because this compact block is easier to transport, easier to handle, and easier to destroy further. And what comes next is far more violent. The crushed block moves toward the heart of the facility, the shredder. This is the most dramatic stage of the entire operation. A hammer mill powered by thousands of horsepower. Inside, massive rotating shafts spin heavy steel hammers at incredible speeds. When the flattened car drops inside, there is no hesitation. The hammers strike repeatedly with overwhelming force. Panels tear apart. The frame fractures. Steel beams snap. What once took months to engineer is destroyed in seconds. The sound is thunderous, metal colliding, grinding, breaking apart. Within moments, the vehicle is reduced to fist-sized fragments. It's intense. It's loud. It's raw mechanical power at its peak. But even this chaos is calculated, because the goal isn't destruction for its own sake. It's material recovery, and that requires precision. The shredded material flows onto conveyor belts, stretching across the facility. At first glance, it looks like metallic debris, but advanced separation systems now take over. Powerful overhead magnets pull ferrous metals, primarily steel, away from the mix instantly. The steel literally jumps upward toward the magnet, separating itself from lighter materials. Next come eddy current separators. These systems create magnetic fields that repel non-ferrous metals like aluminum, pushing them into separate collection streams. Air classification systems blow away plastics, foam, dust, and insulation. Vibrating screens sort fragments by size. Layer by layer, the mixture becomes cleaner. What remains is high-quality steel scrap. But even this isn't ready yet. It still carries paint residues, rust particles, and microscopic contaminants. To truly transform, it must face extreme heat. The prepared scrap is loaded into a giant electric arc furnace. 3 enormous graphite electrodes descend from above. When electricity surges between them, a blinding arc ignites, brighter than the sun. Temperatures climb beyond 1,600 degrees Celsius, hotter than molten lava. The steel begins to glow deep red, then orange, then almost white. Solid fragments collapse into liquid metal. The structure of the old car is completely erased. Identity dissolves in fire. What remains is a glowing pool of molten steel. Sparks erupt. Heat radiates outward. It's both destructive and mesmerizing. But melting alone isn't enough, because steel must meet strict chemical standards before it can be reused. Inside the furnace, impurities separate and rise to the surface, forming a layer known as slag. This slag traps unwanted elements, dirt, oxides, excess carbon. Oxygen is injected to fine-tune the carbon content. Alloying elements may be added to achieve specific mechanical properties. The chemistry of steel determines everything: strength, flexibility, durability, resistance to corrosion. Metallurgists monitor the composition in real time using advanced sensors and sampling techniques. Small adjustments make enormous differences in performance. Only when the molten steel meets exact specifications does it move forward. The destruction phase is complete. The engineering phase begins. The refined molten steel is poured into a massive ladle and transported to a continuous casting machine. Here it flows into water-cooled molds. The outer layer solidifies instantly, while the interior remains molten. As the steel moves through rollers and cooling zones, it gradually transforms into solid slabs, billets, or blooms, depending on the final application. Glowing red beams emerge, moving slowly along the production line. What was once a crushed and shredded car is now a uniform, engineered steel product, ready for shaping. But shaping requires immense force. The solidified slabs enter rolling mills, enormous machines with rotating cylinders that compress and stretch the steel repeatedly. Each pass refines the dimensions further. Thickness decreases, length increases, surfaces smooth out. Controlled cooling ensures the desired microstructure forms inside the metal. Depending on its intended purpose, the recycled steel may become structural beams for buildings, reinforcement bars for concrete, steel coils for appliances, or sheets that will form the body of a brand new car. The cycle continues. Here's what makes this process extraordinary. Steel is infinitely recyclable. Unlike many materials, it does not degrade when melted and reused. Its atomic structure remains intact. That means the steel from a vehicle built decades ago can return as part of a modern skyscraper or a newly manufactured automobile. Nothing is wasted. Not the frame, not the chassis, not the panels that once traveled highways. They are transformed, refined, and reborn. Inside these massive facilities, destruction is not the end. It is the beginning of another life cycle. The next time you see steel rising into the skyline or feel the smooth surface of a new car door, remember this: that steel may have once carried passengers across cities. It may have once been part of a completely different machine. Steel never truly dies. It evolves, again and again and again. If you're fascinated by massive machines, extreme industrial processes, and the incredible journey from destruction to rebirth, make sure to subscribe.